Let's see one more example of runtime library interpositioning. So it is prepared it as a test 2 and test 3, and also the target program, test 2 and 3 are target program, and share the library that we want to put in between the actual library is prepared in my malloc 1 and my malloc 2. So let's check my malloc. Let's check from the test 2. This is the one we found in the slide, malloc and free. And here we have another similar one, test3.c. And test 3, as you can find in here, had two different things. First one is that it involves a printf, and in addition with that, it executes a function f, and inside of the f there is an malloc, but you see here that there is a memory leak. One pointer is allocated, but it's never deallocated, so there is a memory leak. So here we want to have runtime interpositioning for malloc and free, such that we can detect memory leak. Memory leak is allocated but never release the memory at the end of the program execution. If memories are that, then we find there is a memory leak in a program. Okay. And here, once you check the maker file, test 2 and test 3 are compiled in an ordinary manner. And let's first check the my malloc library that is programmed in my malloc.c. This is actually exercise of textbook example, not the text example, the example that we saw from the slide, what we just checked. So here it loads, it links to the DLC, and since we use RTLD next, currently loaded the library. This is something that is given from this dynamic linking library, so we don't need to open a new one, open a specific library, but we are here referring the system library that's already loaded in the system. So here we are finding a function pointer to the malloc and get this one in the malloc p, and actually malloc p is executed. And then what we want to do is printing out the result malloc to the screen. But instead of using the printf, I here use sn printf and fputs. Sn printf is similar to the printf, but the generated string by this pattern and arguments, and this one does not go to the standard output, but it will be stored in the array buff as it is given in here. So this is a printf for string. In that sense, this is s, and n means here we bound up to 50. The string should be written, can be written. So this is s and printf. And then this string will be sent to the standard adder. The buffer's contents are going to the standard adder through the fputs. Fputs get this string and push that into the file, and here the file descriptor is standard adder, so the message will be printed on the standard adder. And so does for the free. The same, but instead of a printf, here use a sn printf and fputs. And let me execute this program. If we call simply execute the test2, then nothing appear. But if I here Yes. And test 2. Then, yes, this is the example that we have checked from the text, the slide. And I think the same for test 3. Yes. Test 3 has a hello in connection with it. So, and it's just pretty similar. And why do I use the print? Why didn't use the printf, but here I use the smprintf and then fpus. So let me replace the implementation slightly. So that I here printf the malloc. Here let me use the printf directly. Then the behavior will be the same, right? Rebuild it and execute the program. Segmentation fault happens. Why? And the issue is that, interesting issue is that printf, inside of the printf, it invokes malloc. Printf, inside of the printf, it invokes malloc. So that malloc is this malloc again. So inside of the malloc execution, printf can execute the malloc so that it executes the malloc again, that it executes the printf. So infinite loop, infinite recursion happens by this effect because printf has an malloc. And the execution of the malloc by printf is also replaced by this malloc. Yes, that's an issue. So we cannot make this recursive execution of the malloc. So instead of the printf, I here call the alternatives. So this is has the same effect as the printf, but it doesn't invoke the malloc, so it's just saved. So check this one. So if we check the source code of the test number 3, we here have a printf hello, right? Hello, and then malloc free. So let me execute our let me bind our malloc library with test number 3, and you will see that before printing out the hello, one malloc was executed, and that was by what? By inside of the printf. Malloc, one malloc was there, and it was invoked. So we check that printf has actually internally invoked the malloc by this example. And we here see that, okay, this address been allocated, and it was allocated, but only this one get free. So we here see that, okay, it doesn't have a match, neither for this one, right? So here we can find that there were more number of the malloc than the free. So it might be a hint of it's a kind of a hint of a memory leak error. That's what this program indicates. But what if we want to have more information? We want to get more information that will be used for debugging. So we here see that, okay, I see there is a memory leak mismatch between the malloc and free, but I want to know at which line the malloc was invoked and what's the malloc, which malloc was not paired it with the free and cause a memory leak. We want to get more debugging information with it. So in order to support that, I here made another malloc alternative at my malloc 2. Let's see this example. Yes, it's a bit complicated, but carefully follows, then you can understand. The malloc logics are pretty much the same, and let's check the free first, because malloc is pretty similar, but it is a different. But free is quite the same, and so if basically looking for the free function from the system library, and then print out which address has been invoked with the free by the target program and printing out that address. Okay, and for the free, we don't need to print out from which location. But for malloc, we want to print out from which program location the malloc was invoked. Because if we only when we had that information, then we can find out which malloc call was not properly matched with the free. And how can we get the line number information? Here, let me introduce one API. Here, things are pretty much the same. So let's check up to here. malloc, my malloc, malloc p, and we here retrieve the actual malloc and put the function pointer malloc p. Things are pretty much the same, and here we call actual malloc, and the next step is we need to print out this PTL value. And printing out the PTL value, so this is a printing out of the PTL value. fprintf standard error, we here print out malloc, allocate this amount of the memory to this pointer value. That's pretty similar, but in addition with that, we here use another library called backtrace. Backtrace is a special library by which we can get the current stack information, the function call stack. At there, we can find out which location the function get executed. So we can retrieve the caller location of this malloc function call. So for example, backtrace array 10, then the value will be given returned into ARR pointer. So 10 pointer will be given up to 10, and actual number is given in here. This is information for the stack. Okay. And then we can replace this stack information with the string value by calling backtrace symbol. Okay. And here, let me print out the stack trace such that we iterated over up to the SG and printed out this is the stack number from 0 to SG minus 1, and then here we are printing out some string that contains stack information for each function call. So let me first show you how the result goes. So make, okay, and for this test3, instead of the my malloc, let me replace it as a my malloc2. Yes, wow, this is the result. And once you carefully see, malloc, for this malloc inside of the printf, this was the stack trace at the moment that malloc got executed. So on the top is the malloc function in our shared library that we have just created, and the location for that malloc function is given in here, and the callers are these location. I think this is in part of the printf. Yes, it's under the libc. It's interesting, isn't it? And the printf was invoked by test3 at this location, and these are all the actual address. By the way, this is all logical address. None of them are physical address anyway. But anyway, these are the address for the function call. So each one will actually represent. So here, test3, this location actually maps to specific code location, but the information is not yet given. So this is actual location. Actual location here means actual memory location for certain function, but we do not know which function it is and which line number it is as itself. Okay. Anyway, that is the case for this first malloc inside of the printf, and after that we have two malloc. So for this malloc, this is the stack trace, and this malloc, this is the stack trace. And let's check cat malloc cat test3. C, and you will find here that this is the first malloc after hello, and it corresponds to this one. So I think this is a main function. So this is the line number, this one, this line number. And the next one is inside of function f. So this line number is now appeared in here. Yes, this will be the line number for actual location. And you will see that stack trace is printed in this manner. Yes, so it will be very informative, right? But you will saw that there are some complicated codes surrounding this printing message printing, and let me explain about why they are needed. Okay, so here I have prepared one static variable of an malloc. Yes, this is a local. It's a bit complicated, so let's go through one by one. So this is a local variable and malloc. So the scope is under the malloc function call, but it is declared as a static variable. And have you ever learned the static variable, static local variable? And how is that goes? And if a local variable is declared as a static, then it becomes kind of a global variable. But no other function can refer it because it's declared inside of a function. But it's a static, which means that the location is assigned it at data section. So it becomes global variable, but it's limited to be accessed by malloc only. So here I'm kind of creating global variable malloc whose initial value is 0. And what's more interesting thing is this keyword. I think not many of you ever seen this one before. underbar thread. And you can find more information for this underbar thread keyword at this URL. And this is a thread local variable, which means that per thread we are creating new global variable and for an malloc. So if there are two threads that are executed together for malloc, then per thread we are assigning a new variable and malloc, which is a kind of a global variable, so that the malloc behave per function. Yes, why it is given in here. So I here intend that malloc can be executed in multi-threaded context. Okay, and what's the malloc represent? Malloc represent the time, how many times malloc get executed. What's that? Why we need that? So it starts from 0, and since malloc got executed, so malloc is incremented in here, and why it is used in here, and malloc is decremented before the malloc function get returned. Why it is used in here? So it counting on how many times malloc got executed and why. So it become either 1 or 0, and why it is needed. And you will see that this logic is guarded by the condition that malloc is a 1. So when malloc get first executed inside of 10, then it'll be 0 to 1, so it'll be executed. But then what is the other case? What's the case when malloc become more than 1? This is important because inside of this printf and inside of this backtrace and backtrace symbol function execution, malloc is used. So if we don't guard this portion of code with this condition, then infinite loop, infinite recursive call happens again. But in this time, I'm here using malloc, introducing malloc counter, and condition this portion of the code to be executed by only very first time of the malloc, so that the infinite recursion never happen by this guard. And if I don't put this condition, then infinite loop happens. Infinite recursion happens. But since only for very first time of the malloc, the printing goes happen, so that for example, fprintf, inside of it, malloc is invoked again, then this piece of code get recursion, but at this moment, and malloc become now 2. So it skip over this part. So no bad thing happen. This is the kind of a trick to get avoided to avoid this infinite recursion. Okay, that is one thing. Okay, so we were succeeded in printing out this stack information, but what's missing here is that we have a stack information and we have a address in terms of the memory location, but it doesn't tell us which line number it represents. And that information can be retrieved by another tool called addr2 line. As its name indicates, it translates address to line number. And here we give -e. -e can indicate the target program. So here, test3. And here we give address. This one, for example. Yeah, this address. Then this tool return the string, this location. Oh, this one corresponding to line number 5 over test3 under this path. Line number 5, what's the line number 5? And then you will see this one actually is a line number 5. In this way, we can precisely identify which line number, at which line number this malloc has been called, and this location that were assigned by this malloc can never freed, and it is a kind of the cause of a memory leak. We can identify by analyzing this log of a target program execution. This is how one case where runtime interpositioning can be used for finding out some bug, especially memory error.